Managing IoT devices at scale is still messy. These devices are often constrained, limited bandwidth, low power, and intermittent connectivity. These conditions make reliable configuration and management a real challenge. And if you look at existing solutions like NETCONF and RESTCONF, they weren't built for this. They rely on heavier encodings like XML or JSON, and run over SSH or HTTP, which are too heavy for constrained environments. This is where CORECONF comes in. It provides a lightweight network management protocol using CoAP for transport, CBOR for encoding, and YANG for modeling. So it keeps the familiar data modeling from the IETF ecosystem, but adapts the protocol stack for constrained IoT environments. So CORECONF solves the efficiency problem, but it introduces a developer usability problem. Working with it directly is painful. Values in raw bytes, numbers instead of readable names, no easy way to inspect your data. PyCORECONF fixes that. We have developed this CORECONF implementation to give you a clean Python interface on top of CORECONF, so you work with YANG names and JSON, and PyCORECONF handles the CBOR encoding and SID translation for you. Let's be more specific about the problem. CORECONF uses CBOR, a binary encoding that is up to 10 times smaller than JSON. Great for the network. But the moment you want to debug a value or write a test, you are staring at hex values and integers. Those integers are SIDs, schema item identifiers. Every YANG node gets a unique number. Efficient on the wire, unreadable for humans. And if a SID changes during development, everything breaks. PyCORECONF lets you forget about SIDs entirely. You write JSON with YANG names, PyCORECONF does the rest. In practice, you don't want to traverse binary trees or numeric paths. You want to query data like you would in NETCONF or RESTCONF. PyCORECONF lets you do exactly that, using XPath-like expressions based on standard YANG paths defined in RFC 7950. A path like this one points to the value leaf across all transducer entries. Add a predicate to target one specific entry. Readable, precise, and directly mapped to the CBOR data store. So far, we've seen what PyCORECONF lets you do from a user perspective. Readable data, intuitive navigation with XPath. The question is, how does it actually work without YANG modules at runtime? The answer is a single artifact, the extended SID file. A standard SID file maps each YANG node to a number. The extended version adds what PyCORECONF needs. The type of each leaf, to convert between CBOR integers and JSON strings, and a key mapping section that tells which leaves are the keys of each YANG list. This matters because CBOR and JSON represent YANG types differently. An identity ref is a SID integer in CBOR, but a prefix string in JSON. An enumeration is an integer in CBOR, but a label in JSON. Without type information, conversion is impossible. The key mapping also tells PyCORECONF how to identify list entries, enabling XPath navigation using only the SID file. Without this, applications risk misinterpreting data or failing to interoperate. You can generate the extended SID file with only one extra flag, sid-extension. Now let's look at the code. You can find the demo in the PyCORECONF repository in the data store sample. It works with the CORECONF M2M YANG module, a weather station model with 12 transducer types: temperature, humidity, wind speed, solar radiation, and more. 4 examples, from the simplest to the most powerful: loading and encoding data. This is what the device or gateway would do before sending data over the network. First, we load the SID file and create a CORECONF model. That one line gives you everything. The model knows all the YANG nodes, their types, the list keys. No YANG module needed at runtime. Now encode the JSON data store to CBOR. The JSON file contains all 12 transducers with realistic values. After encoding, the result is roughly 1/5 the size, and that is before any SCHC compression. This is the whole point of CORECONF. Decode and round trip. Now the other direction. This is typically what a controller or cloud backend does. Take the raw CBOR bytes and decode back to JSON. PyCORECONF resolves every SID back to its YANG name, converts CBOR integers back to identity strings and enum labels, and returns a clean Python dictionary, identical to the input. A lossless round trip. What goes in as JSON comes back as JSON. The CBOR on the wire is purely internal. Your code never has to touch it. XPath read and write. Load the configuration into a data store. Then, read and write individual nodes using XPath. This is equivalent to reading or modifying operational state in a managed device. Iterate with predicates. Finally, the most powerful feature, predicates. This is critical for automation at scale. You don't hardcode device structure. In a real deployment, a data store has many list entries, one per transducer, one per interface, one per sensor. You often need to apply the same operation to all of them, without knowing their keys in advance. Predicates returns all the key predicates present in the data store for a given list path. Then you loop. All 12 transducers updated. No hard-coded keys, no manual iteration over CBOR map. This is exactly what a network management agent does on a live device, and PyCORECONF makes it a 4-line loop. This is PyCORECONF. Young names, XPath navigation, clean Python API, and full CBOR encoding under the hood. And more importantly, this makes CORECONF actually usable in production tooling. It bridges the gap between constrained protocols and a developer-friendly experience. The code, the sid-extension tool, and the RFC references are all in the description. Thank you for watching.
Thanks, PyCORECONF.